Hi, I want to analyze this common emitter amplifier again using the technique that I call analysis by table. Once you get good at doing the hand analysis from the last time, solving those circuits symbolically, and then getting a sense of what the numbers are, you'll be doing analysis by table because you see the patterns in how these amplifiers. In fact, why we call a common emitter amplifier a common emitter amplifier, because just has certain properties all amplifiers of structure have. So how do we do this? First off, we have to figure out which one is which, or what we have here. So here's our structure. This input source. Signal comes from there. It's not part of my amplifier. It interacts with it, but this comes from someone else. My load is over here, represented by just a resistor here, but it could be something else. A loudspeaker would also have inductance and a little capacitance. In the middle is my amplifier itself. From the last time, we have been considering C out as a big fat capacitor, CE is a big fat capacitor, and also CN is a big fat capacitor. Partly, that's for convenience, to be honest, but it's also a recognition of the purpose that these capacitors serve, usually. They all have these sideways capacitors operate as high-pass filters. DC does not go through a capacitor. Signals do go through at some frequencies. When we say this is a BFC, this means we're just considering that CN is large enough capacitance that it looks like a short circuit any frequency that we're interested in, especially compared to the resistance's vicinity. Same thing for this one. It looks like a short circuit at any frequency that we're interested in, which means RE is going to get shorted out when we approximate this as a short circuit, which then makes it easier to analyze, and then we would have an AC 0 at the emitter node of this transistor. Remember what happens with AC equivalent circuits. This node, or this voltage source, is DC and independent. It gets set up to be a 0, and then that also means, because of this short circuit on the left side, that this is also an AC 0, so we redraw the circuit. This analysis by table doesn't necessarily need to redraw this, although it's useful. I won't do it for now. How do we do this? Well, first up, we found our input. Our input happens here. This is a short circuit. Short circuit. This is a short circuit. That's a short circuit. I need to find my input resistance of this amplifier. My input resistance is indeed looking this way. We're in. Output resistance looks from the load back to the amplifier. That would be looking to the left. R out. And then my voltage gain, this one here, down here is V out. Here to here is V in. Signal lowercase, lowercase. You notice how I'm kind of drawing my lines in between this capacitor. Are these capacitors part of the amplifier, or are they part of the source and the load? Oh, I don't know. We call these coupling capacitors because they make the connections between the parts. Right now it's a BFC, so it's a short circuit. We don't have to deal with any filtering from those. Next up, we switch over to agnd.net, or the electronics tour book, rather. It looks like this, agnd.net/tourbook. The table 10 now, sometimes the numbers change. Bipolar single transistor amplifier types. Input is on the base, output is on the collector for us. We've identified that. We call this a common emitter amplifier because input and the output. Its ZI is in fact beta plus 1, little r, little e, plus big Z, big Okay. What's that mean? Oh, okay. Ran is beta plus 1 little re plus d. Okay. Whatever does that mean? Let's go back. Let's look up all of these terms: beta plus 1, re, and ze. All the way up to beta. Remember, beta is the collector current divided by the emitter current. I can go back up one more, but that's beta for the transistor. We'll say it's 100 now. Maybe we'll say it's 99. We have beta plus 1. Using 99 makes it easy. All right, so next up, that was beta. What else? This is RE. Little r, little e. Here it is. Little r, little e. Its name is called the intrinsic emitter resistance. It has a value of alpha VT over IC. Little r, little e is alpha VT over IC. Well, alpha or VT is Boltzmann's constant times temperature in Kelvin divided by electronic charge or elementary charge. And we'll say this is 26 millivolts at 300 Kelvin. Commonly used 26 millivolts. Sometimes we use 25 millivolts. That's all it is. It's just a constant. Alpha is the same as beta over beta plus 1. So if beta is 99, then this is 0.99, so it's near 1. Many times we approximate alpha as 1. IC is the current flowing into the collector at DC. At DC is important. If we look at this circuit, this capacitor now at DC is an open circuit. This C out is an open circuit. This CE is also an open circuit at DC, so if I just cover all this up, I have a 4 resistor circuit here. I can find the collector current, and I can find all the node voltages by doing hand analysis or simulating or find that. We'll just presume that we either have done that or we would if we in fact wanted it badly enough. Okay, so that's Rn. I don't know, does this help us out? Maybe, maybe not. I want to show you a substitution here. So remember, this is beta plus 1. Re is alpha VT over IC. That's nice. So that's alpha, which is beta over beta plus 1. So I'm going to say beta over beta plus 1 times VT over IC. Okay. And then ZE. What is ZE? I hope you see that this beta plus 1 and this beta plus 1 are going to cancel out. So bring it inside. And that's the idea. ZE. ZE is a little different. Go up to our circuit here. Then I'm going to switch back to the tour book. Go down to our definition of ZE. It is the impedance of the bias network at the emitter node looking away from the transistor, does not include source or load impedances. What does that mean? Well, remember, let's look at a common emitter. Here's an NPN transistor. I stand at the emitter node. I put my back to the emitter, and I look out. What impedance do I have? Look at that. CE. Look here, and I look out. CE. Remember, this is a big fat capacitor at any frequency of interest. CE then is looking into a RE in parallel with a short circuit. ZE in this case is 0. That's really awesome because now RE is or Rn is beta Vt over C. Okay, that's great. Let's go back. Go back up. Seen this before. Look at this. Intrinsic base resistance, beta Vt over Ic. That shows up. I have that. Well, I can just replace my beta Vt Ic with R pi, which we saw last time. There we go. So this is R. Oh man, I did it wrong. This is not Rn. This is Di. I didn't even follow my own table properly. Right, so here is Rn. Zi is the impedance right at the base. Right at the base, looking into my common emitter amplifier, that is Zi. Rn is one step back. You can see that it is Zi in parallel with the combination R1, R2. Here we go. Rn is R1, R2, which is the impedance of that bias network. And that whole thing is in parallel with Zi. I can substitute this in, and we have R1 parallel R2 parallel R. You don't have to make the substitution R pi, but it's handy to know because we get this. I just like to show you that when we looked at the input resistance from our other hand calculations, we found Rn, and it was R1, R2, R pi parallel. We got the same thing. That's the whole point. Okay, so next, let's look at R out. R out. Okay. Here is this. I need a new definition. I'm going to draw this right here carefully. This is ZO. Table. ZO, the impedance, into the transistor output terminal, but does not include the bias network. When I say bias network, what I'm talking about is this. Any of the other stuff outside of the transistor itself. Right now it's only RC. Okay. Actually, we should say does not include the bias network or the load, because the load is separate. It's part of our amplifier. So ZO, looking into that terminal, it's not R out. Distinction here. R out includes RC. It's not ZO. All right, so what is ZO? Go back to our table. Down. ZO is RO plus 1 plus A0 times ZE in parallel with R pi. All right, do it. Here we go. R little o plus 1 plus A0, whatever that is, times ZE parallel with other stuff. But wait a second. Wait a second. I already saw that ZE was 0 because ZE, the impedance standing at the emitter with your back to it looking out. In our particular case here, it's 0. Ooh, this is good news. Super, super good news. Why is it good news? Because ZE is now 0. Well, 0 in parallel with anything, I don't care, is also 0. Yeah. So there's a whole bunch of other stuff there. R pi plus ZB in parallel with ZS. All 0 doesn't matter because ZE is 0. Remember how you see A0 and you're like, what is that? It doesn't matter because it's multiplied by 0. Awesome. So ZO is merely little r low. Okay. Back to our amplifier. R out, if we look backwards into this, we're going to see ZO in parallel with RC. Draw this gold amplifier. Here's R out. ZO is looking into my amplifier this way. That is ZO. Just RO in this particular case. That because our R out is now ZO or RO in parallel with RC. So here we go. R out is ZO in parallel with RC, which worked out to be RO parallel with R. And that, from our other analysis, was RO parallel with RC. Two things are exactly the same. Next up, AV0. Space here with my keyboard. AV0, we look this up in the table. We see in the table, we see minus alpha DO in parallel with ZE plus RE. Ooh, all right, well, minus alpha, I can do that. That, you do you. Right, my minus alpha. ZO, what was ZO? I'm just going to substitute, I'll just put it in here. ZO parallel with ZC all over ZE plus little r, little e. Remember, this was 0. This was little r, little o. Alpha is beta over beta plus 1 if we want to switch from alpha to beta. This one is up here, little r, little e is alpha VT over C. Okay, alpha VT over IC. All that's left is ZC. Back to definitions. ZC is the impedance of the bias network at the collector node looking away from the transistor, but it does not include source or load impedances. Look at this. So we're going to look at ZO and we're going to look out now. Okay. ZC, it's the impedance with your back at the collector looking out. I see an RC. I look over here and I see an R load, but remember, our definition does not include that. All that's left is RC. So this is R. Substitute this in, I get minus alpha little r little o parallel RC divided by alpha VT over IC. Oh, look. Yep. Alphas go away. I get minus IC over VT. Then I have RO parallel R Charlie. That looks all good. This is a constant as long as temperature stays constant. This is my DC current. It shows up in my AC analysis. I want to show you IC over VT. We have a name for that. Scroll up. IC over VT is in fact the transconductance, which has the symbol GM. We've seen the symbol GM before. This is equals minus GM RO parallel RC parenthesis around here because it's not times RO is a V0. Let's look at what we had for the last time. We ended up with minus GM RO parallel RC. Moral of this story: The moral of this story is we can do analysis by table if we do it properly according to the definitions and kind of strictly. We will get exactly the same results as we get if we do this by computing the small signal model and then just doing linear circuit theory, finding the input resistance, the output resistance, and the open circuit voltage gain. Having an equivalent output. Thanks for watching.